In this video we're going to look at the least squares regression line. And so what I've got is I've taken the example which we used earlier where we looked at the product moment correlation coefficient for these, and we're basically going to have a look at it again. Now obviously as I plot these points, what the question that I'm asking basically is, if for example I take 3 points and we'll put one a little bit off center, and this effectively, don't forget, restricts what we've got, because I don't know whether my line of best fit could look like that, or could be through all three, because I could be totally wrong with one of the points. But the line of best fit, if I add in a fourth point, generally speaking, is going to go through, and let's just add in a fourth point now, going to go something like that. That's an awful line of best fit, but you get the idea. In fact, that's a shocking line of best fit. Now, the question is, does it look like that, or does it look just that slightly bit further off? There's something wrong with this board, because that's a straight line I'm drawing. Look at that. Now, the question then becomes is, where have I gone wrong? Have I got this one wrong? Have I got this one wrong? Have I got this part wrong? And that's what we look at. And so if I were to take this actual graph and plot it on a page, this is what it would look like. Now, we've seen this before. Now, obviously I'm going to get a computer to do the line of best fit and then talk about how the computer's done it. So if you hang on a sec. So here I've got the line of best fit and I've got the points as well. I've left the points highlighted on purpose because actually I'm going to use them now. Now, what we're looking at is we're trying to find out effectively our the distance between our points and, I can't even think of the word, our points and the line of best fit. That's the one I'm looking for. Now, if I take these distances, now there's a couple of ways you can do it. If I have my line of best fit here and I have a point there, I could look at this distance away vertically from here. I could also look at that distance away. Now ideally, really, I'd want that distance, the shortest distance between the line of best fit and the point. That's going to be quite hard to do though, because I don't know the line of best fit at the moment. So what I'm going to concentrate on is I'm going to concentrate on this, which will give me a y on x. The other way, if I looked at the horizontal sides, that gives me an x on y regression line. Now the reason I'm looking for the y on x is because I'm looking at the variables that I've got. Now I've got maths and English, which are not necessarily dependent variables, but generally speaking, from your science in Key Stage 4 and in Key Stage 5 if you do it, what we do is we put our independent variable on this axis and we put our dependent variable on that, i.e. the y is based on the x. So y on x means y being based on the x value. Now obviously it's not going to be the case for all of these, but for this I'm going to assume that they are based, just because it'll make it much easier for myself. So if I get rid of all of those, what I can now do is then have a look and find the distances between each of these points. Now that's going to be tiny, but that's a little better. Obviously these are meant to be straight lines. I don't have a ruler, and I'm not sure how to use a ruler on this thing. And so there are the values I'm looking at. Now each one of these is called a residual, and the residuals are actually labelled with epsilon. So epsilon 1, epsilon 2, epsilon 3, 4, 5, 6, 7, 8, 9. And what we're looking at doing is we're looking at basically making sure that the sum total of all of those values comes out to be as small as possible. Sorry about that. Now because of the, where was I? Yeah, to find the least value of all of these, so I want these distances to be the shortest possible. Now because of the problem of some being above the line, some being below the line, we end up with these negative values, and much like we did in S1, rather than just find the modulus of it, what we tend to do is we tend to square it. And so what I'm going to be looking for is, if I take my first value, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them, plus my second value, plus my third value, plus my fourth value, so on and so forth, all the way up to my 10th value. Actually, if they're all minimized, then I should end up, hopefully, them all cancelling each other out. But I want to make sure they're as small as possible, because they're never going to cancel each other out, because I've got this line of best fit in the middle. So what I'm going to do is square each of them. And so actually what I'm trying to do is to find out when this value here isn't necessarily equal to anything, but when it is as minimum as possible. Now, the maths behind that, it's not actually that hard. In essence, each of the values, so we'll take this value here, that's actually going to be my y coordinate minus the equation of my line of best fit. Now the equation of my line of best fit is actually going to be in the form of a plus bx, where a and b, a being my y-intercept, b being my gradient, they're two values that we don't yet know. We do know the y-coordinate because it's the y-coordinate of this particular point. And the x-coordinate here is the x-coordinate of that particular point. And so if you have a look at Appendix 4 in your textbook, it'll go through the entire process of that. Feel free to ask any questions if you're not too sure about how to follow it. But the sum total comes up with is the formula that you're going to need, which is y minus y bar is sxy over sxx x minus x bar. And that gives us the line of least regression, the least squares regression line. Now, obviously, for that, we're going to need to calculate a few things. Y bar, x bar, sxy, and sxx. And you know that sxy, well, that is equal to the sum of xy minus n x bar y bar, and sxx sigma x squared minus n x bar squared. So I'm going to need x bar, y bar, sigma xy, and sigma x squared. And to do that with my little table up here, well, I've lost my little table. To do that with my little table, all I need to do is just plug it all into a nice little spreadsheet. Now again, you've got calculators, and I'll do little videos on how to do it with the calculators, but that's all you're going to need. So if I was to start doing this with this one, let's call the maths mark x and the English mark y, then in that case, if I want x bar and y bar, well, I've got them filled out already. So the next thing I do is x times y, so that times that. And again, copy all of that down and sum total all of those. And the next one I'm going to need is x squared. Oops. And so there are my values. Now n, again, is just 10 in this case, because there's only 10 values. So it works very much the same as you do with your product moment correlation coefficient in terms of calculating sxx and sxy. And like I said, the actual maths of how to jump from adding the least value for all of these squareds into there to get to that is in Appendix 4 of the 3rd edition of S2. Don't know what edition you're going to be on, but effectively that's what it is. Now, in the example that I've got no idea what the actual value and answer is. But if you have a look at exercise 4.4, example 4.4 rather, then I go through step by step, one of them putting in all the numbers, so on and so forth. Just one last point as well. When you actually do have your least squares regression line, one thing to note is previously what I drew was I drew my x bar, so I said x was 58.1, and I drew my y bar, so I said y was 59.6, and they crossed. Now notice this time I've still done it, and this time they cross, but my line of best fit also crosses through that point. Because what you're going to have to do is actually draw one of these, and when you draw one of these, making it pass through the centroid actually helps you quite a lot, because you know what the equation is going to be, you know where it's going to cross on the y-axis. But what happens if, for example, I move my graph and I don't have it starting at 0, 0? Straight away your y-intercept's gone, and it makes it that much harder. But because you are only going to do interpolation, can't remember, then effectively this area, can I do a box? So this area is where you've got data for, and you will always have your centroid in the area you've got data for. So if you can get your line of best fit to pass through the centroid, then life becomes that much easier, because you only then have to worry about the gradient side of things.